After completing this lesson, you will be able to define MapReduce, explain the characteristics of MapReduce, understand advanced MapReduce, define Sqoop and its uses, analyze importing and exporting of data from Hadoop using Sqoop, understand the basics of Sqoop 2. Why MapReduce? Prior to 2004, huge amounts of data was stored on single servers. If any program ran a query for data stored on multiple servers, logical integration of search results and analysis of data was a nightmare, not to mention the massive efforts and expenses that were involved. The threat of data loss, challenge of data backup, and reduced scalability resulted in the issue snowballing into a crisis of sorts. To counter this, Google introduced MapReduce in December 2004, and the analysis of datasets were done in less than 10 minutes rather than 8 to 10 days. Queries could run simultaneously on multiple servers and now logically integrate search results and analyze data in real time. The USPs of MapReduce are its fault tolerance and scalability. What is MapReduce? MapReduce is a programming model that processes and analyzes huge datasets logically into separate clusters. While Map sorts the data, Reduce segregates the data into logical clusters, thus removing bad data and retaining necessary information. Nutri is a well-known courier facility. It transports documents across the globe. When the reception staff receive a courier, they color-code it based on the country to which it has to be sent. The dispatch staff then segregate the courier by the tagged color code. Hence, the reception functions as Map and the dispatch team as Reduce. The MapReduce steps listed here represent manual vote counting after an election as an analogy. Step 1. Each poll booth's ballot papers are counted by a teller. This is a pre-MapReduce step called input splitting. Step 2. Tellers of all booths count the ballot papers in parallel. As multiple tellers working on a single job, the job execution time will be faster. This is called the map method. Step 3. The ballot count of each booth under the Assembly and Parliament seats position is found, and the total count for the candidates is generated. This is known as Reduce method. Thus, Map and Reduce help to execute the job quicker than an individual counter. As you've seen in the previous screen, analogy of vote counting is an example to understand the use of MapReduce. The key reason to perform mapping and reducing is to speed up job execution of a specific process. This can be done by splitting a process into a number of tasks, thus enabling parallelism. If one person counts all the ballot papers and waits for others to finish the ballot count, it could take a month to receive the election results. When many people count the ballot simultaneously, the results are obtained in 1 or 2 days. This is how MapReduce works. In this screen, the MapReduce operation is explained using a real-time problem. The job is to perform a word count on the given paragraph. The sentence is, "This quick brown fox jumps over a lazy dog. A dog is a man's best friend." The MapReduce process consists of inputting, splitting, mapping, shuffling, and reducing phases. The input phase refers to providing data for which the MapReduce process is to be performed. The sentence is used as the input here. The splitting phase refers to converting a job submitted by the client into a number of tasks. In this example, the job is to split into 2 tasks. The mapping phase refers to generating a key value pair for the input. Since this example is about counting words, the sentence is split into words using the substring method to generate words from lines. The mapping phase will ensure that the words generated are converted into keys, and a default value of 1 is allotted to each key. The shuffling phase refers to sorting the data based on the keys. As shown on the screen, the words are sorted in ascending order. The last phase is the reducing phase. In this phase, the data is reduced based on the repeated keys by incrementing the value. The word dog and the letter A are repeated. Therefore, the reducer will delete the key and increase the value depending on the number of occurrences of this key. This is how the MapReduce operation is performed. Map execution consists of 5 phases: map phase, partition phase, shuffle phase, sort phase, and reduce phase. In the map phase, the assigned input split is read from HDFS, where a split could be a file block by default. Furthermore, input is parsed into records as key-value pairs. The map function is applied to each record to return 0 or more new records. These intermediate outputs are stored in the local file system as a file. They are sorted first by bucket number and then by a key. At the end of the map phase, information is sent to the master node after its completion. In the partition phase, each mapper must determine which reducer will receive each output. For any key, regardless of which mapper instance generated it, the destination partition is the same. Note that the number of partitions will be equal to the number of reducers. In the shuffle phase, input data is fetched from all map tasks for the portion corresponding to the reduce tasks bucket. In the sort phase, a merge sort of all map outputs occurs in a single run. In the reduce phase, a user-defined reduce function is applied to the merged run. The arguments are a key and the corresponding list of values. The output is written to a file in HDFS. The mappers on each of the nodes are assigned to each input split of blocks. Based on the input format, the record reader reads the split as a key-value pair. The map function is applied to each record to return 0 or more new records. These intermediate outputs are stored in the file system as a file. Thereafter, the partitioner assigns the records to a reducer. In the shuffling phase, the intermediate key-value pairs are exchanged by all nodes. The key-value pairs are then sorted by applying the key and reduce function. The output is stored in HDFS based on the specified output format. The essentials of each MapReduce phase are shown on the screen. The job input is specified in key-value pairs. Each job consists of 2 stages. First, a user-defined map function is applied to each input record to produce a list of intermediate key-value pairs. Second, a user-defined reduce function is called once for each distinct key in the map output. Then the list of intermediate values associated with that key is passed. The number of reduce tasks can be defined by the users. Each reduce task is assigned to a set of record groups, which are intermediate records corresponding to a group of keys. For each group, a user-defined reduce function is applied to the recorded values. The reduce tasks read from every map task, and each read returns the record groups for that reduce task. Note that the reduce phase cannot start until all mappers have finished processing. A job is a full MapReduce program, which typically causes multiple map and reduce functions to be run in parallel over the life of the program. Many copies of map and reduce functions are forked for parallel processing across the input dataset. A task is a map or reduce function executed on a subset of data. With this understanding of job and task, the application master and node manager functions become easy to comprehend. The application master is responsible for the execution of single application or MapReduce job. It divides the job requests into tasks and assigns those tasks to node managers running on the slave node. The node manager has a number of dynamically created resource containers. The size of a container depends on the amount of resources it contains, such as memory, CPU, disk, and network I/O. It executes map and reduce tasks by launching these containers when instructed by the MapReduce application master. The map process is an initial step to process individual input records in parallel. The reduce process is all about summating the output with a defined goal as coded in business logic. Node Manager keeps track of individual map tasks and can run in parallel. A map job runs as part of a container execution by Node Manager on a particular data node. The application master keeps track of a MapReduce job. The flow diagram represents the Hadoop job work interaction. Initially, a Hadoop MapReduce job is submitted by a client in the form of an input file or a number of input split of files containing data. MapReduce Application Master distributes the input split to separate node managers. MapReduce Application Master coordinates with the node managers. MapReduce Application Master resubmits the tasks to an alternate node manager if the data node fails. Resource Manager gathers the final output and informs the client of success or failure status. Let's look at some MapReduce characteristics. MapReduce is designed to handle very large-scale data in the range of petabytes and exabytes. It works well on write once and read many data, also known as worm data. MapReduce allows parallelism. The map and reduce operations are performed by the same processor. Operations are provisioned near the data as data locality is preferred. Commodity hardware and storage is leveraged in MapReduce. The runtime takes care of splitting and moving data for operations. Some of the real-time uses of MapReduce are as follows. Simple algorithms such as grep, text indexing, and reverse indexing. Data-intensive computing such as sorting. Data mining operations like Bayesian classification. Search engine operations like keyword indexing, ad rendering, and page ranking. Enterprise analytics. Gaussian analytics for locating extraterrestrial objects in astronomy. Semantic web and Web 3.0. Ensure that all Hadoop services are live and running. This can be verified in 2 steps. Use the command jps and then look for all 5 services: name node, data node, node manager, resource manager. Small data consists of block sizes lesser than 256 megabytes. To upload small and big data, you will use the following sources: War and Peace, which is from an ebook website. Weather data that is updated on an hourly basis. The sample data set from these sources will be provided and can be used to perform MapReduce operations. Uploading small data and big data. The command to upload any data, big or small, from the local system to HDFS is Hadoop space fs space copy from local space source file address space destination file address. Let's look at the steps to build a MapReduce program. Determine if the data can be made parallel and solved using MapReduce. For example, you need to analyze whether the data is write once, read many, or worm in nature. Design and implement a solution as mapper and reducer classes. Compile the source code with Hadoop core and package the code as jar executable. Configure the application job as to the number of mapper and reducer tasks and to the number of input and output streams. Load the data or use it on previously available data, then launch and monitor the job. Study the results. The user or developer is required to set up the framework with the following parameters: locations of the job input in the distributed file system, locations of the job output in the distributed file system, input format, output format, class containing the map function, class containing the reduce function, which is optional. If a job does not need a reduce function, there is no need to specify a reducer class. The framework will partition the input, schedule, and execute map tasks across the cluster. If requested, it will sort the results of the map task, and it will execute the reduce tasks with the map output. The final output will be moved to the output directory, and the job status will be reported to the user. The image shows the set of classes under the user supply and framework supply. User supply refers to the set of Java classes and methods provided to a Java developer for developing Hadoop MapReduce applications. Framework supply refers to defining the workflow of a job, which is followed by all Hadoop services. As shown in the image, the user provides the input location and the input format as required by the program logic. Once the resource manager accepts the input, a specific job is divided into tasks by application master. Each task is then assigned to an individual node manager. Once the assignment is complete, the node manager will start the map task. It performs shuffling, partitioning, and sorting for individual map outputs. Once the sorting is complete, Reducer starts the merging process. This is also called the reduce task. The final step is collecting the output, which is performed once all the individual tasks are reduced. This reduction is based on programming logic. The basic user or developer responsibilities of MapReduce are setting up the job, specifying the input location, and ensuring the input is in the expected format and location. The framework responsibilities of MapReduce are as follows: distributing jobs among the application master and node manager nodes of the cluster, running the map operation, performing the shuffling and sorting operations, reducing phases, placing the output in the output directory, and informing the user of the job completion status. To install Eclipse in the Ubuntu desktop 14.04, open Ubuntu Software Center. Type Eclipse in the search bar as shown on the screen. Select Eclipse from the list. Next, click the Install button to continue. Once Eclipse is installed in your system, create a new project and add the essential jar files to run MapReduce programs. To create a new project, click the File menu. Select New Project. Alternatively, press Ctrl-N to start the wizard of a new project. Select Java Project from the list. Then click the Next button to continue. Type the project name as word count and click the Next button to continue. Include jar files from the Hadoop framework to ensure the programs locate the dependencies to one location. Under the Libraries tab, click the Add External Jars button to add the essential jar files. After adding the jar files, click the Finish button to create the project successfully. Setting up Eclipse environment for MapReduce. In this demo, you will learn to set up an Eclipse environment to execute a MapReduce program. Double-click the Eclipse exe file to start the Eclipse environment. You will be asked for the workspace where the program will be kept. Click OK. As you can see, there are multiple projects already present, and these projects have their project files and other details. You can also refer to any of the old projects. For the purpose of this demo, let's create a new project. Create a new project. Click File, New, Java Project. Give the name of the project. Let's say Simplilearn. Click Next. Finish. It will create a Simplilearn folder for you. You can see that an SRC directory and a JRE system library are available for you. Now you need to import a few jar files through which Eclipse will understand Hadoop program. To import jar files, perform the following steps. Right-click Simplilearn folder. Navigate to Build Path. Select the Configure Build Path. Click Add External Jars. Go to /user/library/Hadoop directory. You can see that there are multiple jars available. You will need Hadoop Common and Hadoop Core, which you will find inside the Client 0.20 directory. You will notice Hadoop Common and Hadoop Core.jar file. Select the files Hadoop Common and Hadoop Core. Click Apply, and then OK. You will notice these jar files appearing in your reference library directory. Now you need to create a new class in this project where you will write your first program. Right-click the SRC folder. Navigate to New, Class. Give the name of the class file, which can be word count in this case. Click Finish. This has created a blank file, wordcount.java. This brings you to the end of the demo. In this demo, you have learned to set up an Eclipse environment, create a project, and the steps to import jar files. You have also learned to write a program in a class. Running MapReduce program. In this demo, you will learn how to write a MapReduce program in the Eclipse environment. Let's import all the Hadoop libraries that are required to execute this program. In this program, you will calculate the number of times each word occurs in a file that resides in the HDFS directory. You will write two functions, mapper and reducer, that will help you to achieve this task. In the main function, you will have to define the properties and configurations to run a MapReduce program. After you finish writing the program, right-click Simplilearn Project Directory, click Export, and select Jar File under Java. Type the name of the jar file. You can provide any name of your choice. Let's keep it wordcount.jar in this case. Click Finish. Since the file already exists, you will have to overwrite it. So, click Yes. It will create the file in the local directory. You can see the file wordcount.jar in the directory. In order to run this program, let's type Hadoop jar, and then the name of the jar file, wordcount.jar, that we have just created. Then, type the name of the class file. It is inside the Simplilearn package, .wordcount. Now you need to provide input HDFS path, which is simplilearn/simplilearn.txt. You also need to provide an output path, which can be in simplilearn/out_simplylearn. This out_Simplilearn will be a new directory that will be created in HDFS. Now let's go to Hue. Click Simplilearn.txt. Notice that the operation is done on the Simplilearn.txt file. Let's come out of it. You will notice that there is a new directory, out_Simplilearn, which has just been created. This file will have all the counts of the words. This brings you to the end of this demo. You have now learned to write a MapReduce program and run it.
It is important to check whether the machine setup can perform MapReduce operations. To verify this, use the example jar files deployed by Hadoop. This can be done by running the command shown on the screen. Before executing this command, ensure that the words.txt file resides in the data/first location. This image shows the MapReduce version 2.7 architecture comprising Yarn. Hadoop MapReduce uses data types to work with user-given mappers and reducers. The data is read from files into mappers and emitted by mappers to reducers. Processed data is sent back by the reducers. Data emitted by reducers goes into output files. At every step, data is stored in Java objects. Let us now understand the writable data types in advanced MapReduce. In the Hadoop environment, all the input and output objects across the network must obey the writable interface, which allows Hadoop to read and write in a serialized form for transmission. Let's look at Hadoop interfaces in some more detail. The interfaces in Hadoop are writable and writable comparable. As you've already seen, a writable interface allows Hadoop to read and write data in a serialized form for transmission. A writable interface consists of two methods. Read and write fields are shown here. A writable comparable interface extends the writable interface so the data can be used as a key and not as a value. As shown here, the writable comparable implements two methods, compare_to and hashcode. Let's now examine various data types in Hadoop and their functions. The first data type is text. The function of this data type is to store string data. The integer writable data type stores integer data. Long writable, as the name suggests, stores long data. Similarly, other data types are float writable for storing float data and double writable for storing double data. There is also Boolean writable and byte writable data types. Null writable is a placeholder when a value is not needed. The illustration here shows a sample data type you can create on your own. This data type will need you to implement a writable interface. MapReduce can specify how its input is to be read by defining an input format. The table lists some of the classes of input formats provided by the Hadoop framework. Let's look at each of them. The first class is Key Value Text Input Format, which is used to create a single key-value pair per line. Text input format is used to create a program considering a key as the line number and the value as the line itself. N-line input format is similar to text input format, except that there are n number of lines that make an input split. Multi-file input format is used to implement an input format that aggregates multiple files into one split. For the class sequence file input format to be implemented, the input file must be a Hadoop sequence file,
which contains serialized key-value pairs. Now that you have completed input formats in MapReduce, let us look into the classes for MapReduce output format. The first class is the default output format, text output format. It records as lines of text. Each key-value pair is separated by a tab character. This can be customized using the MapReduce text output format separator property. The corresponding input format is key-value text input format. Sequence file output format writes sequence files to save output. This represents a compact and compressed version of normal data blocks. Sequence file, as binary output format, is responsible for writing key-value pairs that are in a raw binary format into a sequential file container. Map file output format writes map files as the output. The keys in a map file are added in a specific order. The reducer then emits keys in the sorted order. Multiple text output format writes data to multiple files whose names are derived from output keys and values. Multiple sequence file output format creates output in multiple files in a compressed form. Distributed cache is a Hadoop feature to cache files needed by applications. A distributed cache helps boost efficiency when a MapReduce task needs access to common data. Allows a cluster node to read the imported files from its local file system instead of retrieving the files from other cluster nodes. Allows both single files and archives like zip and tar.gz. Copies files only to slave nodes. If there are no slave nodes in the cluster, then distributed cache copies the files to the master node. Allows access to the cached files from the mapper or reducer applications to make sure that the current working directory is added into the application path. Allows referencing of the cached files as though they are present in the current working directory. Here are the steps to use distributed cache in Hadoop. First, set up the cache by copying the requisite files to the file system. Set up the application's job config as shown. Use the cached files in the mapper or reducer. Joins are relational constructs that can be used to combine relations. In MapReduce, joins are applicable in situations where you have two or more datasets you want to combine. A join is performed either in the map phase or in the reduce phase by taking advantage of the MapReduce sort-merge architecture. The various join patterns available in MapReduce are reduce side join, replicated join, composite join, and Cartesian Product. A reduce side join is used for joining two or more large datasets with the same foreign key with any kind of join operation. A replicated join is a map side join that works in situations where one of the datasets is small enough to cache. A composite join is a map side join used on very large formatted input datasets, sorted and partitioned by a foreign key. A Cartesian product is a map side join where every single record is paired up with another dataset. A reduce side join works in the following ways. The mapper prepares for join operations. It takes each input record from every dataset and emits a foreign key record pair. The reducer performs a join operation where it collects the values of each input group into temporary lists. The temporary lists are then iterated over, and the records from both sets are joined. A reduce side join can be used when multiple large datasets are being joined by a foreign key, when flexibility is needed to execute any join operation, when a large amount of network bandwidth is available, and when there is no limitation on the size of the datasets. A SQL analogy of a reduce side join is given on the screen. In the output of a reduce side join, the number of part files equals the number of reduce tasks. A replicated join is a map-only pattern that works as follows. It reads all files from the distributed cache and stores them into in-memory lookup tables. The mapper processes each record and joins it with the data stored in memory. there is no data shuffled to the reduce phase. The mapper provides the final output. Replicated joins should be used when all datasets, except for the largest one, can fit into the main memory of each map task that is limited by Java Virtual Machine or JVM heap size, and when there is a need for an inner join or a left outer join, with the large input dataset being the left part of the operation. A SQL analogy of a replicated join is given on the screen. In the output of a replicated join, the number of part files equals the number of map tasks. A composite join is a map-only pattern working in the following ways. All datasets are divided into the same number of partitions. Each partition of the dataset is sorted by a foreign key, and all the foreign keys reside in the associated partition of each dataset. Two values are retrieved from the input tuple associated with each dataset based on the foreign key and the output to the file system. Composite joins should be used when all datasets are sufficiently large and when there is a need for an inner join or a full outer join. A SQL analogy of a composite join is displayed on the screen. In the output of a composite join, the number of part files equals the number of map tasks. A Cartesian product is a map-only pattern that works in the following ways. Datasets are split into multiple partitions. Each partition is fed to one or more mappers. For example, in the image shown here, split A1 and A2 are fed to 3 mappers each. A record reader reads every record of input split associated with the mapper. The mapper simply pairs every record of a dataset with every record of all other datasets. A Cartesian product should be used when there is a need to analyze relationship between all pairs of individual records and when there are no constraints on the execution time. In the output of a Cartesian product, every possible tuple combination from the input records is represented. Sqoop. Now that you have learned about MapReduce, let's talk about Sqoop in Hadoop. Sqoop is an Apache Hadoop ecosystem project. It is a command line interface application for transferring data between relational databases and Hadoop. It supports incremental loads of a single table or a free-form SQL query. Imports can also be used to populate tables in Hive or HBase. Exports can be used to put data from Hadoop into a relational database. While companies across industries are trying to move from structured relational databases like MySQL, Teradata, Netezza, and so on to Hadoop, there were concerns about the ease of transitioning existing databases. It was challenging to load bulk data into Hadoop or access it from MapReduce. Users had to consider data consistency, production system resource consumption, and data preparation. Data transfers using scripts was both time-consuming and inefficient. Direct access of data from external systems was also complicated. This was resolved with the introduction of Sqoop. Sqoop allows smooth import and export of data from structured databases. Along with Uzi, Sqoop helps in scheduling and automating import and export tasks. Sqoop in real life can be used in online marketers. Coupon.com uses Sqoop to exchange data between Hadoop and the IBM Netezza data warehouse appliance. The organization can query its structured databases and transfer the results into Hadoop using Sqoop. The Apollo Group, an education company, also uses Sqoop to extract data from databases, as well as to inject the results from Hadoop jobs back into relational databases. Sqoop is an Apache Hadoop ecosystem project. Its responsibility is to import or export operations across relational databases like MySQL, MS SQL, and Oracle to HDFS. Let's discuss the various reasons for using Sqoop. SQL servers are deployed worldwide. A SQL server is the primary way to accept the data from a user. Nightly processing is being done on SQL servers for years. Sqoop allows you to move data from traditional SQL DB to Hadoop HDFS, as Hadoop makes its way into enterprises. Transferring the data using automated scripts is inefficient and time-consuming. Hence, Sqoop is used. Traditional DB has reporting, data visualization, and other enterprise built-in applications. However, to handle large data, you need an ecosystem. The need to bring the process data from Hadoop HDFS to the applications like Database Engine or web services is satisfied by Sqoop. Sqoop is required when a database is imported from a relational database, RDB, to Hadoop or vice versa. A relational database, or RDB, refers to any data in a structured format. Databases in MySQL or Oracle are examples of RDB. While exporting databases from a relational database to Hadoop, users must consider consistency of data, consumption of production system resources, and preparation of data for provisioning downstream pipeline. While importing the database from Hadoop to a relational database, users must keep in mind that directly accessing data residing on external systems within a MapReduce framework complicates applications. It also exposes the production system to excessive loads originating from cluster nodes. Hence, Sqoop is required in both scenarios. Let's look at the benefits of using Sqoop. It transfers data from Hadoop to an RDB and vice versa. It transforms data in Hadoop with the help of MapReduce or Hive without extra coding. It is used to import data from an RDB, such as SQL, MySQL, or Oracle, into the Hadoop Distributed File System, or HDFS. It exports data back to the RDB. Following is a summary of Sqoop processing. It runs in a Hadoop cluster. It imports data from the RDB or NoSQL DB to Hadoop. It has access to the Hadoop core, which helps in using mappers to slice the incoming data into unstructured formats and place the data in HDFS. It exports data back into RDB, ensuring that the schema of the data in the database is maintained. Here is an outline of the process. Sqoop performs the execution in 3 steps. First, the dataset being transferred is divided into partitions. Next, a map-only job is launched with individual mappers responsible for transferring a slice of the dataset. Lastly, each record of the data is handled in a type-safe manner as Sqoop uses metadata to infer the data types.
MySQL Basics. In this demo, you will learn how to work with MySQL databases. Type MySQL-U training-P training to connect to MySQL databases. In this command, -u denotes username, which is training, and -p denotes password. In this case, the password is also training. Type show databases if you want to view all the databases present in MySQL. You can see that there is a Simplilearn database available, which will be used in the demo. Type use Simplilearn to enter the Simplilearn database. Now, as you can see, you are inside the database. Type show tables if you want to view all the tables present in the Simplilearn database. Notice that there is an account table present in the Simplilearn database, which will be used in further demos of Sqoop. This brings you to the end of this demo. In this demo, you have learned to connect to a MySQL database, view the tables inside a database, and enter a database.
Use the command shown on the image to import data present in MySQL database using Sqoop, where Simplilearn is the database name and device is the table name. The process of the Sqoop import is summarized on the screen. Sqoop introspects the database to gather the necessary metadata for the data being imported. A map-only Hadoop job is submitted to the cluster by Sqoop. The map-only job performs data transfer using the metadata captured in step 1. The imported data is saved in a directory on HDFS based on the table being imported. Users can specify any alternative directory where the file should be populated. By default, these fields contain comma-delimited fields, with new lines separating the different records. Users can also override the format in which data is copied by explicitly specifying the field separator and recording terminator characters. Further, users can easily import data in Avro data format by specifying the option as Avro data file with the import command. Sqoop supports different data formats for importing data. It also provides several options for tuning the import operation. Let's discuss the process of importing data to Hive and HBase. First, Sqoop takes care of populating the Hive metastore with appropriate metadata for the table, and also invokes the necessary commands to load the table or partition. Next, using Hive import, Sqoop converts the data from the native data types in the external data store into the corresponding types within Hive. Further, Sqoop automatically chooses the native delimiter set used by Hive. If the data being imported has a new line or other Hive delimiter characters in it, Sqoop allows the removal of such characters. The data is then correctly populated for consumption in Hive. Lastly, after the import is completed, the user can operate on table just like any other table in Hive. Now that you have seen the process in importing data into Hive, let's talk about the process involved in importing data into HBase. When data is imported into HBase, Sqoop can populate the data in a particular column family in an HBase table. The HBase table and the column family settings are required to import a table to HBase. Data imported to HBase is converted using its string representation and inserted as UTF 8 bytes. Use the command shown on the screen to import data to HBase. Connect to the database using the first command. Specify the parameters such as username, password, and table name using the second command. Create an HBase table with the column family as specified in MySQL using the third command. Now let's discuss the process of exporting data from Hadoop using Sqoop. Use the command shown in the terminal to export data from Hadoop using Sqoop.
Listing table of MySQL DB through Sqoop. In this demo, you have learned to view all the commands through Sqoop and list the table present in a database through Sqoop. Type Sqoop help to view all the supported commands in Sqoop. Notice that there is a List Tables API that lists the available tables in a database. Now let's see how you can do that with the Sqoop command. Type the command. To do that, you will use the Sqoop List Tables API -- connect, then the connection string to connect to MySQL DB. In this demo, we will use the Simplilearn database. You can list the tables by providing the database name, which is Simplilearn -- username, which is training, and -- password, which is training for the MySQL DB. Notice the result displayed on the screen, accounts. This brings you to the end of this demo. In this demo, you have learned to view all the commands through Sqoop. You have also learned to list the table present in a database through Sqoop.
We need to perform the following steps to export data from Hadoop using Sqoop. First, introspect the database for metadata and transfer the data. Next, transfer the data from HDFS to the DB. Further, Sqoop divides the input data set into splits. It uses individual map tasks to push the splits to the database. Each map task performs this transfer over many transactions to ensure optimal throughput and minimal resource utilization. Now we will look at the various connectors using which we can connect to Sqoop to different databases. The different types of Sqoop connectors are generic JDBC, default Sqoop, and fastpath connectors. The generic JDBC connector can be used to connect to any database that is accessible via JDBC. The default Sqoop connector is designed for specific databases such as MySQL, PostgreSQL, Oracle, SQL Server, and DB2. The fastpath connector specializes in using specific batch tools to transfer data with high throughput. For example, MySQL and PostgreSQL databases. We have learned that Sqoop divides the task into 4 default mappers. Let me explain you how Parallelism helps Sqoop in dividing tasks other than default mappers. By default, Sqoop typically imports data using 4 parallel tasks called mappers. Increasing the number of tasks might improve import speed, but note that each task adds load to your database server. You can influence the number of tasks using the -m or num mappers option. But Sqoop views this only as a hint and might not honor it. In the following screenshot, we set parallelism to 8. Common Sqoop commands are listed on the screen. The first command on the screen is to import the data from the MySQL table Sqoop demo to an HDFS directory. Note -m1, which ensures that there is only one mapper output. In the second command, note that ID is greater than 2, which places a condition on data to be imported. You can also specify a specific SQL query as shown in the third command on the screen, where it says -e select start from Sqoop_demo where ID equals 13. The third command on the screen shows an export function. Please note the hyphens and the double hyphen before driver, connect, username, and password. There are some more commands listed on the screen for your reference.
Importing RDBMS table to HDFS. In this demo, you will learn how to import the table accounts from Simplilearn DB to the default HDFS location. Type HDFS DFS-RM-R accounts to delete the accounts table from this directory. This will remove the accounts table from the default directory if the table exists. Type the command. Now, in order to import the accounts table from MySQL DB to HDFS, you will have to type the Sqoop Import-Connection string for MySQL DB. You will have to provide the Simplilearn database, username for MySQL, password for MySQL, -- table, and the name of the table that you want to import to HDFS. Type HDFS DFS-cat accounts to confirm the creation of this table. As you can see, it shows that a directory named accounts has been created. Type HDFS DFS-ls accounts to view the content of the accounts directory. You will notice that multiple part files have been created. You can view the files by providing the whole file name. Type HDFS DFS-cat accounts/*. So let's view this 000 file. Notice the output displayed on screen, which is the data present in the accounts table. This brings you to the end of this demo. You have now learned to import a table to a default location and to remove a table from the default directory. You have also learned to create a table, confirm its creation, and view the contents of the created table.
This command will list all tables in the Simplilearn database in MySQL. In this screen, let's look at Sqoop's limitations. Client-side architecture does impose some limitations in Sqoop. Client must have JDBC drivers installed for connectivity with RDBMS. Client-side architecture requires connectivity to cluster from client. Users have to specify username and password. It's difficult to integrate a CLI within external application. It is not supported with NoSQL-DB because it is tightly coupled with JDBC semantics. Sqoop 2 is the next generation version of Hadoop. following are the advanced features when compared to Sqoop. Client-server design addresses limitations described earlier. API changes also simplify development of other Sqoop connectors. Client requires connectivity only to the Sqoop server. DB connections are configured on the server by a system administrator. End users no longer need to possess database credentials. Centralized audit trail. Better resource management. Sqoop server is accessible via CLI, REST API, and Web UI. Sqoop 2 is being actively developed. Currently, Sqoop 2 has fewer supported features than Sqoop. Let us now summarize what we've learned in this lesson. MapReduce is a programming model that simultaneously processes and analyzes huge datasets logically into separate clusters. MapReduce execution consists of 5 phases: map phase, partition phase, shuffle phase, sort phase, and reduce phase. Sqoop, an Apache Hadoop ecosystem project, is a command-line interface application for transferring data between relational databases and Hadoop. It is used to import or export operations across relational databases. Sqoop Import-Processes contain 3 phases: gather metadata, submit job to the cluster, and transfer data. Exporting processes of data using Sqoop consists of introspecting the database for metadata and transferring the data from HDFS to DB. Sqoop 2 is the next version of Hadoop.
Hey, want to become an expert in big data? Then subscribe to the Simplilearn channel and click here to watch more such videos. To nerd up and get certified in big data, click here.